Hello friends, this is Avin. Welcome to my channel Avin Tricks. This is the 10th video on haloalkanes and haloarenes. In this video we are going to learn the chemical properties of haloalkanes, that is alkyl halides. Alkyl halides show mainly three varieties of reactions. First one is nucleophilic substitution reactions. Second is elimination reactions. Third one is reaction with metals. We are going to study the reactions of alkyl halides in detail one by one. First I give you introduction of nucleophilic substitution reaction. When halogen atom of alkyl halide, we represent alkyl halide by Rx. When halogen atom of alkyl halide is replaced by nucleophile, we represent nucleophile like this. The reaction in which nucleophile is substituted and halogen atom is replaced is called as nucleophilic substitution reaction. I repeat, a reaction in which nucleophile is substituted and halogen atom is replaced. Such reactions are called as nucleophilic substitution reaction. In nucleophilic substitution reaction, this nucleophile, it forms a new covalent bond with alkyl group and this halogen atom is replaced. As the halogen atom is replaced, the halogen atom is called as leaving group. Halogen atom is called as leaving group. Halogen atom is replaced in the form of halide. If it is chlorine, it is replaced in the form of Cl-, that is chloride. If here we have bromine, it is replaced in the form of Br-, that is bromide. Now I will explain you what is a nucleophile. Nucleophile is a species. Species means an atom or molecule or group of atoms or ions which can donate an electron pair to form a new covalent bond. To form a new covalent bond is known as nucleophile. In other words, nucleophiles are electron rich species. They can attack on positive centers. In case of alkyl halides, we know that the halogen atom is partially negative and alkyl group carbon, that is the carbon atom bonded to halogen atom, is partially positive and it is sp3 hybridized. Nucleophile attacks on this positive center and forms a new covalent bond. As the nucleophile, it attacks on the positive center, therefore it is called as a reagent. What is reagent? Reagent is a reactant which attacks on other reactant. I repeat, what is a reagent? Reagent is a reactant which attack on the other reactant. Here nucleophile, it attacks on the alkyl halide, that is the positive center of alkyl halide, so it is nucleophilic reagent. We call it as nucleophilic reagent. And the reactant on which nucleophile attacks, that is called as substrate. Substrate. I repeat once again, the reactant which attacks on another reactant, it is called as a reagent. And the reactant on which nucleophile attacks, it is called as substrate. Because these two words we use very often in organic chemistry, so I have explained you what is reagent and what is substrate. In nucleophilic substitution reaction, nucleophile can attack on alkyl halide through two different paths. The first path is Sn1 reaction mechanism path and second one is Sn2 reaction mechanism path. We are going to study what is Sn1 reaction and what is Sn2 reaction in detail later. But I will tell you right now here, when the nucleophile will follow Sn1 reaction mechanism path and when the nucleophile will follow Sn2 reaction mechanism path. See, If the carbon atom is attached to the halogen atom has bulkier groups like CH3, CH3. When the carbon atom attached to halogen atom is bounded by bulky groups. Bulky groups means large group like methyl groups. Then the nucleophile will follow Sn1 reaction mechanism path. That means if the tertiary alkyl halide is there, then nucleophilic substitution reaction take place through Sn1 reaction mechanism path. When tertiary alkyl halide is there, then the nucleophilic substitution reaction take place according to Sn1 reaction route. And if the carbon atom is attached to smaller groups like this, here the carbon atom attached to the halogen atom is bonded with small groups, then the nucleophilic substitution reaction take place according to Sn2 reaction mechanism path. We can say that when the alkyl halide is primary alkyl halide, then the nucleophilic substitution is followed by Sn2 reaction mechanism path. If we have primary alkyl halide, this is 1 degree alkyl halide. Here the carbon atom bonded to halogen atom is attached to simple groups. Therefore, the nucleophilic substitution take place according to Sn2 reaction mechanism path. I take one more example. If we take methyl bromide, here carbon atom is attached to halogen atom is bonded with simple atoms like hydrogen, then definitely this alkyl halide follows Sn2 reaction mechanism path. That means what? If bulkier groups are present on the carbon atom, then the nucleophilic substitution reaction take place according to Sn1 reaction mechanism, and if simple atoms are present on carbon atoms, then the nucleophilic substitution reaction take place according to Sn2 reaction mechanism. In other words, tertiary alkyl halides, they undergo Sn1 reaction mechanism, and the primary alkyl halides, they follow Sn2 reaction mechanism path. Then the question arises, what about the secondary alkyl halides? Which path they will follow? Which mechanism they will follow? I explain you here. The secondary alkyl halides, they follow either Sn1 or they follow Sn2 reaction mechanism depending upon the reaction environment. I repeat, the secondary alkyl halides, they follow either Sn1 or Sn2 reaction mechanism path depending upon the reaction conditions or reaction environment. The second type of reaction shown by the alkyl halide is elimination reactions. This is also called as beta elimination reactions. Why it is called as beta elimination? Why it is called as beta elimination? The reason is, see here, the carbon attached to halogen is called as alpha, next beta, next gamma, next delta, next epsilon. In beta elimination, the hydrogen atom from the beta carbon atom and the halogen atom, they are replaced. Therefore, this type of reaction is called as beta elimination reactions or simply elimination reactions. And this elimination reaction, that is beta elimination reaction, is of two types, E1 and E2. That is elimination reaction of first order and elimination reaction of second order. We are going to study in detail what is E1 and E2 reactions later. And the third type of reaction shown by alkyl halide is reaction with metals, that we are going to see it later. Now we are going to learn nucleophilic substitution reaction in detail with examples. The first reaction we will take the reaction of alkyl halide with NaOH or KOH, potassium hydroxide, or silver hydroxide. Before we write the product, we should be able to find which is the nucleophile in this reagent. If you see here NaOH, Na is positive, therefore OH is negative. Therefore OH minus is the nucleophile. If we take KOH, which is the nucleophile, we know that K is a positive and OH minus, it is the nucleophile. In case of AgOH also, Ag is plus and OH is minus. Therefore, in each case, OH minus is the nucleophile here that is going to substitute, that is going to form a new covalent bond with alkyl group, and we get ROH, and the halogen atom is replaced in the form of halide. Halide means X minus. For example, if we take methyl bromide, and if we react this methyl bromide with say KOH, we know that OH minus is the nucleophile that is going to substitute with methyl group, and we get methyl alcohol and we get potassium bromide, that is KBr. And as I have already told you that if the carbon attached to the halogen atom, if it is bonded by small atoms or groups, then that will follow the Sn2 reaction mechanism path. Therefore, this reaction, it obeys or it follows or it passes through Sn2 reaction mechanism. Now I'll take one more example. Now I take CS3, CH3, CS3. This is tertiary butyl bromide, and if we take tertiary butyl bromide, again we are going to get alcohol, that is tertiary butyl alcohol, because the nucleophile OH minus is substituted to the carbon sp3 hybridized carbon. This is sp3 hybridized carbon, and nucleophile attached to that sp3 hybridized positive carbon, and we get tertiary butyl alcohol and KBr. And if you look at this alkyl halide, this carbon atom bonded to halogen atom is surrounded by, or it is bonded or it is attached with bulkier groups, therefore it will follows Sn1 reaction mechanism path. We are going to study in detail what is Sn1 and what is Sn2 reaction mechanism later. When alkyl halides react with NaOH, KOH or AgOH, we get alcohols. And if methyl bromide reacts with KOH, we get methyl alcohol. And if we use tertiary butyl bromide, it reacts with KOH, it gives tertiary butyl alcohol. And this reaction take place according to Sn2 reaction mechanism, and this reaction take place according to Sn1 reaction mechanism. And what is Sn1 reaction mechanism and what is Sn2 reaction mechanism, we are going to study in detail later. Now, reaction of alkyl halide with sodium alkoxide means R-ONA. This is called as sodium alkoxide. Here, which is the nucleophile? As we know, Na is positive, therefore R-O minus is the nucleophile that is going to substitute here, and we get R-O R- plus NaX. We get here ether. This is ROR- is the compound, its name is ether. For example, if I take ethyl bromide, if it is reacted with C2H5ONa, what is the name of this? Sodium ethoxide. Then we get C2H5. This is the nucleophile O dash. This is the nucleophile O C2H5. O C2H5 is the nucleophile, and we get NaBr. This is diethyl ether. The name of this compound is diethyl ether. The next nucleophilic substitution reaction is reaction of alkyl halide with sodium acetalide, that is CH triple bond CNA. This is called as sodium acetalide. Which is the nucleophile in this? We know that Na is positive, therefore this group, that is HC triple bond C minus, is the nucleophile that is going to substitute here. So what we will get? We get here C triple bond C H plus NaX. This is very important reaction. If we want to increase the number of carbon atom in the product side by 2 carbon atoms, we follow this reaction, that is alkyl halide is reacted with the sodium acetalide. So we get the product having 2 carbon atoms more than the reactant. Therefore, this is a step up reaction. For example, if we take methyl chloride, if it is reacted with sodium acetalide, we get CS3 C triple bond CH plus NaCl. If you see here, the reactant has only 1 carbon atom, but product has 3 carbon atoms. Therefore, this is a step up reaction. Now the reaction of alkyl halide with sodium thiol, NaSH. This SH is called as thiol group, and this is sodium thiol. In this, which is the nucleophile? We know Na is positive, therefore SH thiol group is nucleophile. This is substituted, so we get alkane thiol. What is the name? Alkane thiol plus NaX. If we take, for example, ethyl bromide, if we react with the nucleophile sodium thiol, we get C2H5SH plus NaBr. What is the name? Ethane, C, alkane thiol. Therefore, what is here? Alkane, that is ethane thiol. Now the fifth reaction is reaction of alkyl halide with sodium azide, that is NaN3. N3 is called as azide group. And which is the nucleophile here? We know that Na is positive, means N3 must be nucleophile, that is N3 minus. This nucleophile attacks on this alkyl group and we get RN3 and NaX. This is called azide. If we take example, ethyl bromide reacts with sodium azide NaN3, we get ethyl azide, that is C2H5N3 plus NaBr. Now the next reaction is reaction of alkyl halide with Grignard reagent. Grignard reagent is nothing but RMgX. This is called as Grignard's reagent. This is organometallic compound. You have to remember, because here metal is also present and this is organic compound, therefore it is also called as organometallic compound. In this Grignard reagent, the nucleophile is, as we know that Mg is positive and this alkyl group is negative, that attacks as a nucleophile and we get RR' plus MgX2. Here you have to remember that this is alkane. So if we want to convert the alkyl halides into alkanes, we have to use Grignard reagent. For example, if I take ethyl bromide and if I take methyl magnesium bromide as Grignard reagent, this group will attack on this ethyl. I write this ethyl group as CH3, CH2, CH3 plus MgBr2. That means this is nothing but propane. So if we want to prepare the alkanes from alkyl halides, we have to use Grignard reagent. Ethyl bromide can be converted into propane by using methyl magnesium bromide. If we want to convert ethyl bromide into butane, we have to use here ethyl magnesium bromide. According to requirement, we can use different Grignard reagent. Now the reaction of alkyl halide with ammonia. Ammonia means NH3. Here we should be able to find which is the nucleophile in this. We know that H is always positive, so remove one H plus from this. What remains? NH2. Therefore NH2 must be minus, therefore NH2 is nucleophile here, so we get RNH2 plus HX. This H plus will combine with halogen, so we get HX. This is called primary amine. This is 1 degree amine. If we use alkyl halide with, if we react alkyl halide with RNH2, what is the nucleophile here? We have to remove one H plus from this. So what is remain? RNH must be negative. Therefore, this is the nucleophile that is substituted to alkyl group. So we get RNHR. That means this is secondary amine. This is secondary amine plus HX. This is primary amine. Again, if we take the alkyl halide with R2NH. If we react alkyl halide with R2NH, which is the nucleophile here, remove H plus here. So what remains? R2N remains. Therefore, this R2N minus is nucleophile here. So H plus will form HX and the nucleophile attack to this alkyl group. So we get RN R2. This is tertiary amine. So in this way, alkyl halides can be converted into primary amine, secondary amine and tertiary amines. Now the reaction of alkyl halide with sodium salt of acid, that is R-COONA. This is called sodium salt of acid. So here, as we know, Na is positive, therefore R-COO minus will be the nucleophile. So we get R OOC R' plus NaX. This is nothing but ester. So alkyl halides, when they are reacted with sodium salt of acid, we get esters. The next reaction is reaction of alkyl halide with lithium aluminium hydride. Li AlH4. Here nucleophile is H minus. So this H minus, it attacks on alkyl group and we get RH plus X minus. This is nothing but alkane. So if we want to convert alkyl halide into alkane, we have to use the lithium aluminium hydride. If we take an example, if we take ethyl bromide and if we use lithium aluminium hydride, the nucleophile H minus will form C2H6 plus Br minus. This is nothing but alkane. What is the name of this alkane? Ethane. So in this way, alkyl halides can be converted into alkanes by using lithium aluminium hydride. Up to now, we have seen the reactions of alkyl halides with the nucleophile having one nucleophilic center, that is, say, NaOH. In this NaOH, OH minus is the nucleophile. It has only one nucleophilic center, that is, oxygen can donate the electron pair to alkyl group and we get alcohol. But there are certain nucleophiles such as CN, they have two nucleophilic centers. That means they can donate the electron either from carbon or they can donate electron or from nitrogen. If the linkage take place through carbon, then we get alkyl cyanides. If the linkage take place through nitrogen, then we get RNC, that is, we get isocyanides. If the linkage take place through nitrogen, we get, or we call it as isocyanide, and if the linkage with alkyl group take place from the carbon, we get cyanides. Such nucleophiles which have two nucleophilic centers, that means the nucleophiles which have two rich electron centers. Here carbon is also electron rich as well as nitrogen is also electron rich. It can form the linkage with alkyl group either from carbon or from nitrogen. Such nucleophiles which have two nucleophilic centers are called as ambident nucleophiles. This is most important. What is ambident nucleophile? The nucleophiles which have two nucleophilic centers, they can form linkage through two different nucleophilic centers. Such nucleophiles are called as ambident nucleophiles. Let us take another example of ambident ligand, that is No2 group. No2 group exists like this. This is O minus and these are the NO2 group. NO2 group exists like this, O minus and a pair of electrons present on the nitrogen. If we react alkyl halide with NO2, the reaction of alkyl halide with NO2 has two nucleophilic centers. That means it has two electron rich centers. That is, O minus is also electron rich and nitrogen is also electron rich center. Therefore, this species has two electron rich centers. That means it has two nucleophilic centers. Therefore, it is ambident nucleophile. If the linkage take place through oxygen, we get RON double bond O. This is called as alkyl nitrite. If the linkage take place through oxygen, we get nitrites. If linkage take place through nitrogen, then we get, if linkage take place through nitrogen, if the linkage take place through nitrogen, we get nitroalkanes, that is R N double bond O O minus. This is called nitroalkane. If we take here an example, if we take ethyl bromide and this nitrite, if the linkage take place through nitrogen, then we get C2H5NO2, that is nitroethane. We get nitroethane plus Br minus. I repeat, NO2 is an ambident ligand because it has two nucleophilic centers. If the linkage take place through oxygen, we get alkyl nitrites. If the linkage take place through nitrogen, we get nitroalkanes. Now we are going to take examples of ambident ligands with alkyl halides. Now we will see nucleophilic substitution reactions using ambident ligands. When alkyl halide reacts with KCN, as we know that here K is positive and Cn is negative, because this is ionic compound, so it breaks into K plus Cn minus. Here the carbon atom is electron rich, so it forms the bond with alkyl group and we get the RCN, that is we get alkyl cyanide. We get alkyl cyanide. Here this cyanide group is bidentate nucleophile. Here carbon atom is electron rich, therefore it forms a bond with alkyl group and we get alkyl cyanide. If we take for example ethyl bromide, if it is reacted with KCN, definitely we are going to get ethyl cyanide, C2H5CN. That means the bond is formed from the nucleophilic center carbon. So we get cyanide. If we take alkyl halide and if we react with silver cyanide, AgCN, here the very important point we have to remember that the bond between silver atom and this carbon is covalent in nature. It is strong bond. It cannot dissociate or break or ionize into Ag plus and Cl minus. It will not dissociate into Ag plus and Cl minus. Therefore, this carbon is strongly bonded to silver atom. Therefore, this nitrogen now donates electron and forms a bond with alkyl group. So we get RNC. So we get RNC. This is called as alkyl isocyanide. Try to understand this one. If we use potassium cyanide, we get alkyl cyanide. If we use silver cyanide, we get alkyl isocyanide. What is the reason? Here KCN is ionic in nature. It forms the positive and negative ion. Carbon becomes electron rich, so it forms bond with alkyl group, giving alkyl cyanide. In case of AgCN, AgCN is a covalent compound. The bond between Ag and carbon is strong. Therefore, nitrogen, it forms bond with alkyl group. So we get alkyl isocyanide. So this is very, very important. You have to remember, most of the students, they get confusion why KCN gives cyanide and why AgCN gives isocyanide? The simple reason is KCN is ionic compound, therefore the carbon atom is rich nucleophilic center, so it forms bond from carbon. And AgCN is a covalent compound, nitrogen atom is electron rich, therefore it forms bond from nitrogen giving alkyl isocyanides. If you want alkyl cyanides, you have to use reagent potassium cyanide, that is KCN, and if you want isocyanides, you have to use AgCN as the reagent. Now let us take one more ambident ligand, that is NO2. Reaction of alkyl halide with potassium nitrite KNO2. This potassium nitrite is ionic compound, so it dissociates into K plus ON double bond O. Here oxygen is electron rich center, so it forms a bond with alkyl group, so we get alkyl nitrite. And if we use alkyl halide, if it is reacted with silver nitrite, here silver nitrite is a covalent compound. Silver nitrite, it is like this. The silver nitrite is a covalent compound. The silver and oxygen bond is very strong, so the nitrogen, it is electron rich. Nitrogen forms a bond with alkyl group, so we get RN double bond O, O minus. This is the nitroalkane. So if I take an example, ethyl bromide, if I react with AgNO2, then I get nitroethane, C2H5NO2. This is nitroethane. If you want nitrites, you have to use KNO2. If you want nitroalkane, you have to use AgNO2. Once again, I will explain you. NO2 group is ambident nucleophile. It has two nucleophilic sites. It can form a bond either from oxygen or from nitrogen. If you use KNO2, that is potassium nitrite, as the reagent, KNO2 is ionic compound, hence it dissociates into K plus O minus N double bond O. Here oxygen is nucleophilic center, electron rich center, so it forms the bond or linkage with alkyl group through oxygen. So we get alkyl nitrites. If you use AgNO2, the AgNO2 compound is a covalent compound. The bond between Ag and oxygen is very strong. Therefore, the nitrogen, it forms the bond with alkyl group giving nitroalkanes. In this way, we can get nitrites if we use KNO2 and we get nitroalkanes if we use AgNO2. In the next video, we are going to take Sn1 and Sn2 reactions in detail with mechanism. I hope you have enjoyed this video. Please like, share, subscribe to my channel. I am thankful to YouTube and millions of YouTube